Welcome to the lesson on torque and rotational equilibrium. We're going to jump right in here with discussing the torque equation as given on your reference table. The torque equation is tau, lowercase Greek letter, which is a symbol for torque, equals RF sine theta. A couple things here. Torque, the symbol tau is the symbol for torque. R is the symbol for lever arm, which is the distance between the pivot point of the rotation and where the force is applied. And then of course we have F, which you also already know as the force. We'll talk more about the sine theta aspect here in a moment. The units of torque, if you take a look at it, the units of force is newtons, and the units of a lever arm would be meters. So the units of torque are Newton meters, newtons times meters. The other thing that we want to talk about here is that you see that it says tau equals RF sine theta, but being multiplication, the torque equation has a commutative property to it, meaning that the sine theta deals with finding a component of a force perpendicular to the lever arm as written in here, but there are problems in which it's advantageous to find the component of a lever arm that is perpendicular to the force. That comes naturally by this equation because R and F are commutative, meaning it doesn't matter in what order you multiply them. So this equation could easily also be F times R sine theta as opposed to R times F sine theta. Okay, so there's the commutative property of the torque equation with regards to, are we going to take the component of a force perpendicular to the lever arm as indicated in the version on the reference table, or are we going to take a component of a lever arm that is perpendicular to the force? And we'll obviously have more on that as we do problems in this unit. Okay, there are some key concepts here, and if you heard me talk about a little bit already. One is that the lever arm R and the force F must be perpendicular to each other. So what happens here is that this angle theta takes into account, and the trig function sine takes into account, what if they're not? Theta would be measured from the horizontal in order for this to be true. If measured from the vertical, then it would switch to this cosine trig function. But if the force is not perpendicular to the lever arm, and we'll see an example of that in a little bit here, then you would take the vertical component of that force to find the component of the force that is perpendicular. So what we're saying here in this first bullet, this first key concept is that R and F must be perpendicular to each other, and if they're not, then we have to find a component of one or the other that is perpendicular to each other. Okay? Our second key and our third deals with the direction of torque rotation, and it is designated that torque that causes counterclockwise rotation be deemed positive torque rotation, and torque that causes clockwise rotation is deemed negative torque rotation. And if you have a question about why that is, ask in class. All right, moving on, we're going to talk about rotational equilibrium. And this is simply a statement that means the summation of torques that acts on an object is equal to zero. So, similar to translational equilibrium, in which the sum of forces is equal to zero, we have here the sum of the torques acting on a system causes the system to not rotate. Okay, so that means we have torques counteracting each other and keeping the system in rotational equilibrium. We have two examples that we're going to take a look at here, and both of these are the same examples that you're going to be doing homework problems in. Here we have a wrench on a lug nut or some other nut here, And you see here that the force is perpendicular to the lever arm, which is 0.3 meters long. See, the lever arm is the distance from the pivot, where you can imagine the nut is turning there, to where the force is applied along the handle of the wrench. And so this would cause, in the diagram here, this would cause positive torque rotation, because it would cause the wrench to rotate in a counterclockwise direction. Let's also address, what if F was not perpendicular? You can see here that theta would be the angle between that force and the lever arm. And so what we need to do here is take the component of this force, this red force that is perpendicular to the lever arm, and you can see that this would be this dashed line that I'm writing here. And so this would be F sine theta. And that's where that comes from in that torque equation. Okay. Moving over to our beam over here, you'll have a problem on this later as well. We can see that the beam itself is the lever arm, and we have three forces acting on this, none of which are perpendicular to the lever arm itself. And so we have this component of the 30 Newton force that would be perpendicular to the lever arm. We have this component of the 25 Newton force that's perpendicular to the lever arm. And we have this component of the 10 Newton force perpendicular to the lever arm. If we take a look at the diagrams, and how do we calculate this left component, it would be 30 newtons, or 30 sine of 45 degrees. Our component on the center force, since the component is adjacent to the angle, would be 25 cosine of 30 degrees. And the component of the 10 Newton force on the right would be 10 sine, back to sine here, of 20 degrees. So you just have to pay attention to where the angles are in relation to the component that you're trying to calculate that's perpendicular to the lever arm. So not always in our problems is the torque calculated by using the sine function. Sometimes, depending on where they give you the angle, it's calculated by using the cosine function. Next, we're going to talk about intelligently selecting a pivot point. In this problem, you're going to be asked to calculate the rotation, the torque caused by the forces, selecting the pivot point to be at C, as written in blue here, and at O, drawn in green here, and what kind of torque that might cause. There are times in which you're going to do a problem in which you get to freely choose the pivot point. You don't in this particular problem that you're going to do, but there will be problems in which you get to choose the pivot point, and you want to do that intelligently. And the reason, what we mean by that is that you want to select a pivot point that eliminates a force that's unknown causing torque. The reason you would want to do that is if you have more than one force that's unknown, you want to select a pivot point so that you eliminate some of those forces causing torque. And why would that be? That is because that force, when you select, for example, let's say in this problem it was the green pivot point O. If you're going to select O as the pivot point, what you're doing is you're eliminating the 30 Newton force causing any torque. Why is that? Because there's no lever arm distance. There's no lever arm between the 30 Newton force and where it's attached to the pivot point. So what you've done by intelligently selecting O as the pivot point is you've eliminated that force as causing torque. And if that force was unknown, that would be advantageous, an intelligent selection, because you would be able to solve for other aspects of this problem, probably other forces in this problem, if they were either unknown or if you had other things that you had to find in this problem. Okay? I know maybe that's a bit confusing, but you will definitely experience this as we go through and solve some problems here. All right, that's our lesson on torque and rotational equilibrium, and we'll get started right away here with solving some problems.